Or take this trivial thing, which is quite a little toy. Various lengths of slabs of metal fixed at two places in a very special way. Here is a slab of metal fixed right there. Get a view of that right there. This is a xylophone, I suppose. And now when I excite this instrument, here's the way the member vibrates, its principal mode of vibration, and the length and the cross-section determines the pitch of the vibrating member. Some things a little flat there, but the physics is still available to us. Or something quite essentially trivial. Here is a little figure in the shape of a frog, and it has a steel sliver here. And here is another quite like it, but you notice the difference in the sizes of the slivers. There is a wide one, there is a narrow one. Listen now to what emerges when I flex them. Which suggests that the heavier, wider, the one possessed of more inertia, has a lower pitch. So we learn something about the physics of vibrating members by this device. Now, consider a thermal toy, since I suggested I might do something on this program. Here is a little shaft which is geared to a wheel, which turns a disc, and some scraping of a metal is done. And the scraping gives rise to such a high temperature that the metal is made incandescent, and it emits its own light. Watch this. Notice what is happening. I am converting mechanical work to thermal energy. The thermal energy is being commuted to optical energy, or light, a thermal toy. Or another one of the same mechanism. Oh, look at the fire spit out there. No, that isn't fire spitting out. That's a hot little piece of metal. So, question. What kind of metal could we possibly have that gets incandescent with so little work done? So very little work. Another acoustic toy. A pipe. Holes for the fingers. Whoa. I'm not so good a piper. But yet, from a study of this, we can learn how the length of a pipe affects the pitch. Now, an interesting toy. A chamber with a piston and a little stopper which closes the chamber very tightly. I'm going to close it very tightly, and now push the piston in suddenly. Not only is this a thermal toy, but an acoustic one. Why? When I push the piston in rapidly, it gives rise to compression of the air inside, and the temperature rises very high, quite like the temperature rising in the cylinders in a diesel engine, which you know is fired without any ignition system, just from the high temperature arising from compression. So, this thermal energy, the rise, the elevation in pressure, drives the stopper out. And listen. Now I'm going to take one which is a little longer. Do you see? This one is a little longer. And if pipes behave as pipes should, we will find this pitch a little lower. So, and finally, what do we call this? What do you call this thing? An accordion. Yeah, an accordion. I'll not discuss the physics of it. It's a little too elaborate for the time I have here. But I have little levers which can open and close certain orifices. And watch me. Now, I wish I had about an hour to discuss how it is that the sound emerges at different frequencies, at different pitches, or more of the same. which I enjoy very much. Little chambers which have little diaphragms in them and holes here, and I turn this one upside down, and I turn that one upside down, and I turn this one upside down, and now I turn them right side up. And we ask, where do the different pitches or frequencies emerge? And it all has to do with the length of singing pipes. So, finally, what have I? Physics of toys. Acoustic, thermal. Acoustic, thermal. Let me see. Oh, here is a good one. Here is a good one. A little chamber, a little hole in the chamber, a pipe to blow, and a little spin wheel. What am I going to do? I'm going to use some air from my lungs, drive the air in there, it comes out a little hole. Since this is a vibrating chamber, there will be some music, but the energy also of the emerging air will turn the pedal, the spin wheel. Watch it. And the physics of this would take me a half an hour to explore, and I thank you for watching.